here. Okay, so I think, yeah, recording has started. Okay, so let's talk a little bit about word and sentence embeddings in machine learning. When we're talking about word and sentence embeddings, or when we talk about embeddings in general, we're related to machine learning, of course, we're actually talking about turning text, turning words or sentences or even documents, whole documents, into numbers. So when we see the word embeddings, we're just dealing with number or numerical representations of words. Now, the amazing thing about this relatively new technology is that the numbers that represent the words are not arbitrary numbers. They're not just random numbers, as you will see. They reflect the words or the sentence meanings. So in some way, we have managed through machine learning to make these numbers, let's say, contain the meaning or the semantic value of each word or sentence, and which is something amazing. And the most, even more fascinating than that, is that we can also do arithmetic operations with these numbers. So for example, we convert words into numbers, and then we can add words, we can subtract, we can multiply words, exactly as we do with numbers. And not only that, but the result of these operations, like the sum of two words being added together, is actually a new number which corresponds to a specific word. To give you an example, if we get the embeddings for the words boy and girl, and we add them together, we get a new embedding, a new number, which corresponds to the word kids or teenagers. If we get the words boys and girls and add them together, we get the new number, a new embedding, and that embedding reflects the word teenagers. And as you start searching to learn more about these word embeddings, you will probably see this example all around the web. It's actually arithmetical operation with these words. So we get to do these mathematical operations with embeddings. We get the word king, we subtract man, so you can think of taking the meaning of king, subtracting the man, or let's say the gender, from this word, and what we are left with is a numerical representation of the thing that is left after we have subtracted, let's say, the meaning of man, which you can think of this as, let's say, the ruler. If we subtract the gender from the king, we have something like the meaning for a ruler. If we add to that meaning, to that embedding, the word woman, we will get something that combines the meaning of ruler and the woman, the part that's close to the gender, to the female, let's say, gender. And out of this equation, we will get queen. So as you can see, embeddings are a pretty amazing and fascinating topic. So let's dive more into this. The technology that we will use and we will see in this session are, of course, JavaScript, the programming language. We're going to use Tensorflow.js, which is the machine learning library that we will use to see all these things happen. And we're going to use a model, a pre-trained model, to understand and encode sentences, whole sentences, not just words, into numbers or embeddings. This is the machine learning model. Now, a machine learning model can be thought of, let's say, as a trained brain. So for those of you who are not very familiar with machine learning models, a model is simply let's say, some kind of software, some kind of code that has been trained on some kind of patterns. For example, when we get pictures of cats and pictures of dogs, and we put them as input to a machine learning model, and we train that model to understand the difference between cats and dogs, as seen on pictures, of course. After we train that model, you think of it as a little child which learns to understand the difference between photographs of cats and dogs. After the training phase, we have a model, a pre-trained model, as it's called, that we can feed new photographs of cats and dogs, and this model will tell us whether it sees a cat or a dog in a picture. So a model can be thought of as like a very simplistic, let's say, model of a brain, which has been trained to understand very specific patterns. Dogs and cats, handwritten letters, objects in an image, human speech, or anything you can imagine. So moving on to the objectives, we will see how we can understand natural language, human language with machine learning. We're going to encode text, and we are going to turn words and sentences into numbers. We're going to use a bit a more fancy word, which is vectors. We're going to get this word and sentence embeddings out of this encoding process. We're going to see how we can get these embeddings for words, for single words, using a model called word2vec. And then we are going to get introduced to the universal sentence encoder, which is a model that encodes full sentences, not just words, but full sentences. And at the end, we will see a demo where we can improve a question and answering system using the sentence encoder. And excuse me, and then we're going to make this Q&A system more performant and more efficient by understanding the similarity between different sentences, between different questions. So we have to start a little bit by looking at natural language and how this journey of understanding, of making computers understand natural language evolved. So in the beginning, before the machine learning era, the way that we used to process and understand natural language was based mainly on rule-based systems. That is based on grammar or the syntax of the sentences or the words. We get something similar to computer programming languages, which was like if this, then that. And with dictionary-based systems, so we had a word and then the translation of that word in another language. We used statistical models. We still use, of course, these technologies, but there's a limitation to these technologies. For example, ambiguation. How can a model that is trained or that is rule-based can understand whether a word is seen in a different context and what's the meaning of the word in different context? We have another limitation is misspelled words, neologisms, unseen text, something that wasn't that was something new, slang, internet parlance, OMG, LOL, all this new kind of language that's missing from the from the rule-based system. This turns out to prove that these systems have some or lots of limitations. It's also labor-intensive, it's a manual effort, and it's also time-consuming, which means that something was missing at that point. So then came the machine learning revolution. The booming factors for ML in the early 2000s was that we get to have really large data sets, lots and lots of data. We have vast amounts of natural language content, social media, news, articles. We also saw a very big improvement in speed, performance, and rapid growth of machine learning. And we saw some very impressive results in pattern recognition. It was time for AI to take the lead. So in the slides, there will be more notes and descriptions below, so you can press the down arrow to read more about the things that I will describe, and you will also see some reference at the end, but I won't go into these descriptions. I will try to to present them here myself, but you can check them afterwards in the slides. Now, then we moved on to another era, and with machine learning, we had to encode text into numbers or vectors. As you know, computers are digital machines, so we need to feed them numbers. They do not understand pictures, they do not understand words, they do not understand sound. All they understand are numbers, digits. So also in the case of text, we need to convert words into numbers in order for computers to be able to work with this data. So we need to convert them to numbers. There are several approaches that exist on how we can convert a word into a number. We have index-based encoding, which is something like, let's say that giving a random number to a different word, to its word. We have one-hot encoding. We will see some examples in a bit. And we have word embeddings, which is the more advanced version of converting words into numbers. So the first approach, it's just taking a random unique number and assign this number to for each word. For example, if we had the vocabulary or the sentence, a cat and a dog play together, we assign a random number to A, we assign a random number to cat, to end, the same number, of course, to A, to dog, play, and together. And we have like a conversion from words into numbers with a very, very simple scheme. Another technique to encode words into numbers is the one-hot encoding. So for one-hot encoding, what we do at first is take all the unique words that exist in the vocabulary. For example, in the sentence, a cat and a dog play together, we have these 6 unique words. Then for each word, the encoding works as this. We have a vector, which is just a list of 6 numbers. It's the dimensions, as we say, of the vector, which, as you will see, reflect the size of the vocabulary. And for the word that we're using, we are going to use the number 1. So all the words have the same length. All the boxes, you can see, all the places here have a 0, and we get to see the 1 placed on each word of the vocabulary. Together. But these methods have some limitations. First of all, if we have a very large vocabulary, for example, if we use, I don't know, 100,000 words, we will have really, really large vectors. For a vocabulary, for a document or a data set of 100,000 words, we will have 100,000 vectors with 100,000 bits or size each. So it gets pretty big pretty fast. Another thing that's very, very interesting here to note is that both these methods, like one-hot encoding and the index-based encoding, do not capture the meaning of the words. These are just numbers that do not reflect the actual semantics, let's say, of the words. So they're just some arbitrary, you might say, randoms. So this is where we go into something more advanced, which is word embeddings. And this means that we're not going to find a way to encode the meaning of the words inside these numbers. Now things become a little bit more complicated with word embeddings. Word embeddings is a lightweight and unique numerical representation. So we turn words once again into numbers, into a list of numbers for each word. But these numbers get to capture the word's relationship and meaning, the semantics. So they're not just random numbers; they have some relation with the context, with the word's meaning. And so the numbers actually represent something about the word's meaning. I will skip this one. So And these word vectors live in a semantic vector space. What this fancy word means is that these words, these vectors, live in a you can imagine living in a 3D geometrical space. So we can measure the distance between them and also the similarity based on this distance. Each vector is projected into this vector space according to its semantic relationship with other words, the context. So depending on how and when and how often and when we see each word, we place this vector in this vector space, in this geometrical space, according to these properties. So, and we can visualize this space and actually see the semantic relationships. We will see some visual examples. We can apply vector arithmetic on these words. So addition, subtraction, multiplication, calculate the distance. So when we talk about vectors, let's do a quick recap. A vector in mathematics is a geometric object that has magnitude or length and direction. Most of the times when we go to search for a vector, you see something like this. It's sort of like an arrow pointing to a direction and has this length, magnitude. This is our word representations. This is how we're going to encode our words. They will become vectors. Many algebraic operations on real numbers, such as addition, subtraction, multiplication, negation, have close analogies for vectors. I mean, we can do addition, subtraction, multiplication, and so forth with vectors. So they're pretty close to real numbers. A vector, there's a typo here, can be expressed as an array of numbers in JavaScript, like this, an array and a few numbers. A vector of size 2 by 1, so 2 elements in a single row, contains 2 numbers and can be thought of as a point in 2D space. In the same manner, a vector with a dimension of 3 by 1 with 3 values, you can say, we can think of it as a point in 3D space. And then when we move on past the limit of 3 dimensions, we go to 5 or even more dimensions. So vectors can exist in multi-dimensional space. They're not just limited to 3 dimensions, which is the limit that we can we humans can visualize things. According to the distance of these vectors, we can see how close the vectors and also the meaning of the words behind these vectors are. Let's see a very, very simple example for a presentation. We have here the representation, the vectors of 3 words: hamburger, cheeseburger, and Flixbus. You can think of these vectors as a list of numbers. As you can see here, these are just 4 vector numbers, but 4 number vectors, but we can have larger vectors. And if we visualize them as vectors in a, let's say, coordinate system, you will see that the hamburger and cheeseburger vectors have kind of like the same length and also the same direction. So as you can see, the similarity, the semantic similarity, is reflected in this vector representation, whereas this Flixbus is like completely in a different direction. And of course, we see that these 2 words are kind of similar, are closely related to each other. We're kind of getting closer to how we can use word vectors. If we take a large vocabulary and we turn this vocabulary into vectors, we will have something like this, roughly. This is a 2-dimensional space. These are the vectors living in a 2-dimensional space, just to get an idea, a rough idea. So as you can see, all the words are vectors, and we have like this, they have length and they have direction. And vectors of words that are closely related to each other have some kind of a, as you can see, the same length and pointing to the same direction. So the vector cat and the vector dog both point towards the dogs and the cats. England, Paris has the same like direction to France as London has to England. So as you can see, words as represented by as vectors produce this kind of aspects, let's say, and we can calculate the distance of these vectors and also do some arithmetic operations and get some very interesting results. So let's see a vector space in real time. Let me okay. So what you see here is a vocabulary that is turned into vectors. So all these dots, as you can see here in a 3D space, are the words that were found in some reviews for hotels, for movies, I don't remember exactly. But this was like a big text which contained reviews from clients. Like this was a good hotel, this was not a good hotel. I spent, I don't know, many times like waiting in the reception and stuff like that. So we took these words, this vocabulary, these sentences, we ran them through a machine learning model, and we converted them into vectors. And as you can see here, now we kind of like reduce the dimension into 3 dimensions. All these words, let me see if I can, I think we can view them, view these as words. Okay, we can, there's a link missing here, there's a button, but as you can see, the words that have negative value are on one side, and the words that have positive value are placed on the right side. So you can see that their sentiment, let's say the sentiment connected with these words, is also represented in these opposite sides. So let's check some words: original, cool, quickly, reasonably. So these are probably the positive words, the words that were found in positive reviews. And some, you know, they're really a little bit too generic, but worth, need. Whereas if we turn this into the other side of the vector space, we will we'll see words like horrible, not, crap, weighted. So the words that had a negative, let's say, sentiment were placed here. This is how we convert words into vectors, and this is how they are placed in a vector space. Now take this 3-dimensional vector space, give it like hundreds and even thousands of dimensions, and you get word embeddings. Let's go to the next. You can check the embedding projector in a new tab here. So what are the use cases for using word embeddings? First of all, we can calculate the semantic similarity, find the synonyms, find the words that have the same meaning, find the antonyms, find words that have the opposite meaning, recommend, get something like, for example, a word like laptop, find a similar word, and maybe recommend something like this. So if someone is searching for, I'm looking for a laptop battery, we can also use find a similar word to laptop, a word that has a similar meaning, and then also recommend, let's say, an answer in an FAQ or another question and answering system. We can do classification. So we can take like words or sentences or even documents, as we will see later on, and classify them by topic or by gender. So we can get the vocabulary of a book or of a document or even like the whole language vocabulary and classify words based on the gender. So queen, king, woman, man, and so forth, or by topic, sports, politics, or something like that. And we can, I can show you here a screen of a classification. So this is like a visualization of book embeddings. So instead of words, now we have embeddings, vectors of books. And you can see that these embeddings, these vectors, are placed on a 2-dimensional space based on the genre. So we have crime novels clustering here, like this blue group. We have like this, let's say the novels are this orange vectors. The non-fiction books are clustered around here, this green area. We have science fiction. So as you can see, the genre of the book is also reflected in this dimensional space, in this 2D dimensional space, which is kind of amazing because we can visually see what the books are actually about. The semantic clustering is about seeing this kind of same clusters as words here, as word embeddings. So we have some vocabulary, and we get to see like this related to the bathroom, the toilet. These are clustered here. We have like this kitchen, oven, appliances kind of here, the colors. So we get to see clusters forming in these vector spaces. So we get to visualize things, words, and meanings in 2D or 3D space. We can use language translation in a very, very advanced form. So we have what's called cross-lingual word embeddings. I think you will understand by the picture. So we have a vector space of English words. These are the blue words. And so we transform a vocabulary into vectors. Then we take another language or another vocabulary in another language, and we also calculate and create the vectors of this vocabulary. And as you can see, the German words and the English words in this vector space are really, really close to each other. So instead of doing dictionary-based translation, instead of having a list of day equals tag, money equals Geld, and so forth, we just look at the distances between these vectors. When we see that the money vector in the English vector space is close to this point, is close to this vector in the German vector space, we might say that these words will also have the same meaning. So we can see day, tag, information, peace, life, world, and this gives some amazing capabilities to the translation systems. We no longer have to take every single word and translate them in another language. We can work through the vector representation to see how one word is translated into another vector space and subsequently to another language. So amazing things happen. So it's demo time. So we're going to see right now a quick demo for word embeddings. I want you to open this in your browser. I will also send you the source code. So in here, we have loaded the model of English vocabulary, and we have words as embeddings. And we can find, for example, words that are near to some word that we try. So if I write here laptop, and I search in this vector space the vectors that are closest to this word, I get notebook, which has a distance of 0.64, computer, which is a little bit further from the laptop, 67, and as you can see, we have all these very, very close vectors. So these are words closely related to notebook, to laptop. They are either used in the same context, or they are words used to also represent the same meaning. So notebook is used like laptop. This means that if a customer asks for a laptop, let's say cover, or a laptop screen, we might want to see if they meant like a notebook cover, and then recommend something that is in our product list as notebook screen cover, or I don't know. You can try all other words. There are some really interesting results. For example, Godfather will find like the nearest word is Scarface from the book, from the movie. We also see gangster, mafia, Ghostbusters. So feel free to use whatever you want. We have a small vocabulary of 25,000 words, but you can see some very interesting results here. For example, Java will produce, as you can see, operating system, Linux, and at the third place, close to Java is Indonesia. It's actually the country where Java is can be found. Yes, some words are missing from the vocabulary. So if I try some word that's not there, I will get an error. Not only words that don't exist, but maybe some words are missing from this rather small vocabulary. We have like 25,000 words for this demo. Now let's go to Similarity, which is really, really interesting. In here, we are going to compare the similarity between two words, and we will get a percentage here. So if I compare Microsoft and Mango, I will get 12%. There's no, like, they have almost literally no similarity what Microsoft has to do with Mango. But if I say Apple, it will understand that Apple is also a computer company and also an apple and sorry, fruit. So they have a much larger similarity rating here. If I use Microsoft with doors, it will have a low similarity. But if I use it with Windows, you will see that it has a really large similarity percentage. So try, I don't know, Greece with Athens, and you will see some results. Greece with Greek, as you can see, we have like a high percentage. Now, let's go to the more interesting part. Let's try to add vectors together. Now we have addition. So we get boy and girl, we add them together, and we get teenager. If we add boys and girls, we get kids. If we get, now this is interesting, Greece and Turkey, we get Cyprus, because we have both Turkish and Greek people living there. So you can try other things. I have placed something that, some words that I've placed here, like violence, ideology, and we get hatred, which is really interesting. We can also subtract the one vector from another. So if I subtract plural, the word plural, from the vector of the word human, I get humans. If I say, I don't know, Obama, president, now, of course, some results are a little bit, if I subtract president from Obama, I get Clinton. Now this is, let's try Trump, Melania. I don't know if, okay, there's probably an error. There's some word missing from the vocabulary. And now here is really, really interesting. So in this, we're doing both subtraction and addition. So I have the word Italy, the vector for Italy. I subtract Venice, and I add Athens, and I get Greece. We can also try lower, low, and high. So I'm subtracting low from the vector lower, then I add high, and I get higher. With a much larger and better trained vocabulary, you can get some very interesting results. So you can play around with this. You can find the code here, the models, the code that was inspired by the original code. So this is one of the demos. But I'm going to switch to what we're here to see today, which is sentence embeddings. So when we move from word embeddings to sentence embeddings, we are actually converting sentences into vectors. So you can say that a sentence can be multiple word vectors or word embeddings combined together. We get to use some algorithms, and we calculate a vector for a single sentence. And this means that we can represent the meaning of sentences as vectors. So we have like this sentence: I want to cancel my shoes orders. It's of course comprised of word embeddings, small word vectors. We use an algorithm, and we get a vector for this sentence. And we have a model. It's called the Universal Sentence Encoder that does exactly that. It converts sentences into vectors. The Universal Sentence Encoder is a model that encodes text. You can pass any input, any sentence into it, and it will convert it into a 512-dimensional embeddings, meaning that we get a sentence as an input and we get an array of 512 numbers. And these embeddings, which are correlated to the meaning of the sentences, can be used as inputs on natural language processing tasks such as sentiment classification. For example, is this sentence something that has a positive, let's say, a sentiment, or a negative? Of course, we can find if two sentences have a similar context, a similar meaning, which is really so we are going to use Universal Sentence Encoder model with TensorFlow JS. For this, we're going to use a lightweight version of the pre-trained use model, which is rather large, just to load it on the TensorFlow JS, with TensorFlow JS in the browser. You can find the model in the repository in the TensorFlow JS page here. Oops, sorry. Let's not move away from the slides. Okay, so in the official TensorFlow JS page, we can find all these pre-trained models. So instead of training our own model, we can use a model that does image classification, object detection, detect the toxicity in text, and we are going to use the Universal Sentence Encoder. We're taken into a GitHub repository, and we have a description of how we can use this model. So let's dive into the code. Now, let me take a look a little bit at the questions. Now we're going to see how we can construct a vector from a sentence. We can do the same thing with a word. Right now we're going to see the sentence encoder. So I think, Chris, we will see the case of a sentence. So I have VS Code here. I'm going to create a web page. Encoder. And I'm going to open this HTML with in a live server in the browser. I will keep the browser here, and let me make this. Okay. So the first thing we have to do is we have to load the model, TensorFlow JS and the Universal Sentence model. So I will go here, and I will take the script tags. And let me switch them. I'm going a little bit fast because we are running out of time. So I'm going to load both TensorFlow JS and the Universal Sentence Encoder, as you can see from a CDN. Let's make the code a little bit bigger. I'm going to open the console just to see things happening. Now, the first thing I'm going to do is create an asynchronous function called init. I'm going to need a script that. And I'm going to make this async because I'm going to run a lot of asynchronous operation inside this function, and I want to use the wait keyword. So let's run this function. And okay. Let's test that it's working. So it's working. I can see the init here. Now, the first thing I want to do is that once I have loaded this universal sentence encoder model, I have a variable, a global variable called use, which contains everything I need to use with the universal sentence encoder. So this use, as you can see, it's globally available. The version is 1.3.2. I can get some information about the model. But the thing I want to do right now is load the model. So I'm going to use the await keyword and the load method to load the model. Now, as you can see, this command starts downloading the model from the server, and now it has been loaded on the web page. So at this point, I can say that the model has loaded. So model is loading at this point, and the model at this point. So the model is loading, and after a couple of milliseconds, the model is ready for us to use. Now, let's turn some sentences into vectors. So I will add a couple of questions in an array. What is your favorite color, for example? And how old are you? Just to test these two sentences together. And in order to embed them, in order to convert these these sentences into vectors, into embeddings, I'm going to say questions embeddings. I'm going to use another method, a synchronous method from the model, which is the embed. So after a while, I'm going to see the sentences turned into vectors. So let's open the console. Here is the resulting object. Now I cannot really see anything here useful at this point. Here is the shape of the vector. So we have two sentences. So we have two rows, and each row is comprised of 512 numbers. So we have two vectors with a dimension of 512. Now, in order to see these vectors, I can convert them into an array. So I can do that. Questions embeddings array, and I will say question embeddings. And in order to get a tensor, as it is called now, the question embedding is a TensorFlow work with tensor. So it's just these lists, let's say these vectors, these matrices of numbers, this collection of numbers. I can convert them into an array synchronously for now with the array sync. And let's log this. Let's see. Okay, so now I have something closer to what I can see in the console. So as you can see, the question embeddings array now is an array with two vectors, and both vectors have a length of 512. So they are just numbers, as you can see here. It's just a list of numbers. This is a huge, so we cannot really, I will open it. So it's just a list of numbers. This is a vector. This is an embedding of a sentence. This sentence has been converted into a list of 512 numbers. And these numbers have some kind of semantic value to them. They're not just arbitrary numbers. So let's see if we can calculate the distance between these two, between a question that we get from the user and one of these questions. So let's say that we have an FAQ and we have these two questions and their respective answers. And we want the user to enter an input and try to see if we can find a question that is close to what they are asking. So I will say have the input will be what is your age. Okay. The user phrases the question, how old are you, in a different manner. So in order to check to see whether this sentence, this vector, is close or similar to one of these questions, I will have to also turn it into a vector. So, or an embedding. I'm going to get a new vector. Let me now I'm not going to display this. This is just an array of 512 numbers. Now, what I want to do is I want to find a way to calculate how close this sentence, this vector of what is your age, is with either the first question or the second. In order to do that, I'm going to use a method that is implemented in Tensorflow. And this method calculates what is called the dot product. So this is just a mathematical operation. And from the result, we get a number which shows us how close two vectors are to one another. So I'm going to say, I'm going to use the tf dot. I'm going to convert, I'm sorry, to get the dot product of the input embedding. Now, let me say, and the first question embedding, so the first one, let's say here, I'm going to get the first element. So this is the first question. So let's see the number. Let's see if everything worked well. We get to see something that is not very, right now, we cannot see very clearly what the result. That's because this is a tensor. This is in the format of a tensor, and we are going to convert this into a number with the datasync method. Let's wait. So we have a float number, as you can see, which is 0.3. So as you can see, the distance between what is your favorite color and what is your age is close to 0.3. Now let's calculate the distance between the second sentence in the array, which is the vector of the how old are you. I'm going to wait a little bit. And as you can see, the second result of this dot product between these two vectors, between the vector of what is your age and how old are you, it's pretty high. The vector will always be from in the range of 0 to 1, between 0 and 1, so 0.003 up until 0.999. And depending on how high this number is, and we can convert this into a percentage. We can see how closely related these sentences are. So we have 30% and 84%, which means that the second sentence, the second embedding, the second vector, how old are you, is very, very close to the meaning of the vector, the input embedding, which is the what is your age. So let me see the chat here. I've seen many things going out. Okay, so sorry, I'm going to go a little bit quickly through this because I'm going to send you the code behind all these demos. So we saw the demo. That was the similarity between sentences. You can find this source code into this GitHub repository into the demo branch. Here is the code. So it's pretty simple. And I've also created a Git history. So if we go to this branch and see the commits, you can see that the commits are actually step-by-step implementation. So the first commit contains just like loading the library. The second commit, I have placed the description, just creates the async function. So you can also see this code step by step through the commits. And a very, very nice way to visualize this is through an extension called Git File History in VS Code. So I will just quickly I will go to, let me see if I can. So right now I need to run a couple of things here, so I won't be able to do this, to demonstrate this. So we have this demo, which is very simple. And other things that you will see in the slides, because we have to wrap up. We have this demo along with the code. I think this is pretty interesting. You can check out this right now. So what we're doing in this demo is actually taking the code from the previous example and creating our own questions. So for example, if I want to create a new question and also get the vector out of this question, I might say, what is your favorite color? I click add question and it transforms this question into an embedding. I can say, how old are you? What's your intern, or how old is your laptop? So I'm creating these questions, and in this, behind the scenes, we are also embedding these questions, meaning we get the vector representation. Now, if I open the console, you can see that we have like each sentence was, we calculated the embeddings for each sentence, and we have added this question, these embeddings into a list. Now I'm going to ask a question, and it will try to find the sentence with the closest distance, the closest result of the dot product. So how old are you? I will say, what is your age? And you will see that the prediction is for the sentence, how old are you, which is very, very high. It's like 84%. If I ask, how old is your notebook, for example, remember the word embeddings? You will see that we have a prediction of 8% for this sentence. And I don't know, pick a color. So we have a 65%, like a little bit lower, but it's very, very close to the what is your favorite color. Now, if I write something, I don't know, messing around, you will see that we get the closest from this vector is the how old are you, but it's so low, it's like 15%, which makes no sense. So this means that you can, when you're searching to find the appropriate answer or the appropriate, let's say, question, depending on the user's input, you can set a threshold and say if the prediction is lower than, let's say, 50% or 65 or 70 or even 8%, just to be accurate, you can just discard the answer. So this is like really low, so you can just discard this. So this is another demo that you can play around, and you will find the code here on this repository. And going a little bit quickly, I'm sorry, just to give you. Okay, you can add the following questions. Okay, this is a real-life example. Now, this is how we can use TensorFlow.js in a real-life example. So for this, what I did is that I took our FAQ here at Social Hackers Academy. So we have this FAQ page. It's based on WordPress. And we get these questions to see if the student, if a candidate, an applicant is eligible for the course. So we have these questions, which, as you can see, just a bunch of questions, and we want to see, we want the users to search for the appropriate answer. So let's say we have this question: how many months is the course? So with this very basic string similarity algorithm that WordPress uses, I can search for how many months, and I can get the answer. But if I ask something like, what is the duration, I won't get nothing, because this is there is no duration string found here. So this is very simple. Now, what I did was I took all these questions, I calculated the embeddings, the vectors out of these sentences, and then I also calculated the embedding, the vector from the user's input. And let's see the results. Sorry. So let's, okay. So if I now search here, in this code, I have all the embeddings for these questions. And I can now ask not only how many months is the course, which search, and it will give me, as you can see, it has 100% score for the how many months is the course. It will have a similar score to the how much does your course cost, okay, and a lower cost on this one. But if I write something, if I phrase the question in a different way, like what's the duration of the course, you will see that I get a very high percentage score for how many months is the course. So someone phrasing this question in a different way can also get an answer, whereas with this very, very basic string similarity, let's say, algorithm, we don't get to see the answer. For example, what kind of hardware I need, okay? So let's try to see if we can get an answer to the question, what kind of hardware I need. So I will say, what kind of computer? It gets close, but it goes, do I need? It gets close because it finds the kind. It doesn't understand computer, it doesn't find the computer here. So if I say, what kind of computer do I need? I won't get any results. It will just find, or let's say, what computer. So as you can see, I get no results. But if I put this here and calculate the embedding and go into the vector space and see the calculate the distance between this sentence and the other vectors, I get a very, very high score for what kind of hardware I need. Even though I didn't use the word hardware, since the embeddings are close to each other, I get a very high score. Or, as you can see, I don't own a computer. So this is how we can use the TensorFlow JS and machine learning with a model that's trained on natural language, and we can get some really, really interesting results. So you can find all of this. And just quickly, I'm going to skip the improvements right now. The toxicity checker. This is just a demo. I'm just going to show you the demo. It uses TensorFlow JS and the universal sentence encoder to calculate, to predict whether the sentence is toxic. What means toxic? Containing identity attack, insults, toxicity, sexually explicit, threat. So I have created this code pen where I can count the words and the characters, let's say, but I can also enable toxicity check. So right now I'm loading a model for TensorFlow JS. It's going to load the model, and after a while I will hit the check toxicity. It will try to see if the sentence contains some toxic, let's say, sentiment, which contains threat. As you can see, it correctly found that someone is threatening me, and also toxicity. So we can use this in chat systems, we can use it in forums. So for example, if I put a commit message like, your last commit sucked, sorry for this language, and if I try to commit this or place this as a comment in a public forum, I can run this check, and I will find insult and toxicity really high. And then I can run this TensorFlow JS pre-filtering, and I can like remove this this comment. So this is another really, really cool example. This model, the toxicity model, can be found here. This is the text toxicity detection, along with all these other really, really cool models. Now, we have to wrap up this point. So let me skip. Let me go to the chat and see if we have some questions. Let's go to see. I'm going to see. Okay, just a couple of questions I see here in the notes. Which algorithms are used in creating the vector space? So this is a little bit too advanced for now. You can search for word2vec and also find the paper behind the universal sentence encoder to see how they used a machine learning model to train a corpus of text, a big vocabulary, and turn these words into embeddings. How do you construct a vector from a word? We saw how we constructed a vector from a sentence. You can do the same thing with the word2vec demo. Will you share a link for this webinar to watch it later? Yes, you can find all these notes. For example, the links, the references, everything will be placed and updated here. And if you follow the repository that contains these demos and the presentations, as you can see here, we will soon update this link with the recorded video, so you will see the presentation there. So make sure to check this repository. You can also send us a message. Feel free to experiment with TensorFlow JS. I think it's really amazing, an amazing technology, and it's very it's relatively easy to run these models on your web pages or on your web applications. Thank you for attending. Thank you for being here. So make sure to copy the link, and you can send us an email if you want to learn more about Social Hackers Academy, how you can enroll in our courses, and also ask me any questions you have regarding machine learning and TensorFlow JS. So thanks everyone, and see you.